Section 3.2, real zeros of polynomial functions. Okay, so there's two types of zeros to polynomial functions. We have the real ones, which is what we're studying in this section, and then in 3.4, we're going to study the imaginary ones as well, the complex ones. Okay, but for right now, the real ones are the ones that you actually see on the graph of the real number line. Like in the quiz that we just took, we had those zeros. They either bounce, they cross, or they wiggle, right? Okay, so first of all, the terms that we use interchangeably, you have to understand. The roots of a polynomial are the same thing as the zeros of the polynomial. They mean exactly the same thing. Yeah. Zeros and roots are literal synonyms. I can refer to the roots, I can refer to the zeros. I have a tendency to use the word roots more than zeros because that's how I learned it back in the day. But nowadays, more people call them zeros than roots. But that's what they really are. They're where the y values of the graph equals 0. How does that manifest on the graph? Well, that's number 3. That's the x-intercepts. Those are the x-intercepts. So your roots are your zeros, are also your x-intercepts. And as you learned in Algebra 2, because we're doing it right now, I know you learned it, they're also the solutions to the equation when you set the function equal to 0. Okay? They are the values that when you plug it in, give you a 0. Okay? Let's look at a quick example of other types of real roots. Find the simplified exact solutions to the following equation. All right, so you can pretend like this right here with some function f of x, and we set it equal to 0. So if we're trying to find the solutions, we're trying to find the roots of f of x. Would you agree? Okay, so once it's equal to 0, our goal is to factor it. Is this thing already factored? Kind of. Good. It's partially factored. How do we know when it's completely factored when there's variables?
When there's no two, or no coefficient.
No coefficient?
Or one coefficient is 1.
Are we going to be able to factor 2x minus 5 anymore? No, because it's what? Degree what? 1. Okay, so that's the first thing that's a giveaway. Is it a linear factor, mx plus b? Anything that's in the form mx plus b we consider as prime. Let's write that down. A linear factor is prime. Okay, over here. A linear factor, mx plus b, is considered prime. All right, now is x squared minus 5 factorable?
No.
Well, yes, but it is a difference of squares. Is it a difference of two perfect squares? No. Now, if this were x squared plus 5, it would be game over. So let's come over here and talk about another type of prime factor that you might see. A quadratic factor of the form ax squared plus b is also considered prime. Okay? It's the sum of two squares. That's prime. Okay?
Isn't there a factor for the sum of 2 squares?
No. You're thinking of the sum of two cubes. Yeah, the sum of two cubes is factorable. The sum of two squares is not. Okay? Sum of two squares is not. So, x squared minus 5, believe it or not, is factorable. So here's what it would factor into. The 2x minus 5 goes along for the ride. The x squared minus 5 factors into x minus something and x plus something. What do we call those two? X minus, x plus? They multiply to give you a difference of squares, but the two factors themselves are called whatchugets. These are called conjugates of each other. Okay. Now, if 5 were a perfect square like 4, I would put a 2 in each of them, right? But what is the square root of 5? Very good. We just write it as the square root of 5. Okay. It's that easy. It's that easy. So that does factor. Now we can go through and we can rattle off all the roots using the factor theorem. Okay. So the solutions are what? If 2x minus 5 is a factor, what's the corresponding root? 5 halves. Good. You add 5 and divide by 2. 5 halves. If x minus the square root of 5 is the factor, what's the corresponding root? Square root of 5. And similarly, if x plus the square root of 5 is a factor, the corresponding root is? No, not the negative square root of positive 5. Yeah.
Whenever you add the square root of 5, when you do the difference of squares right there,
Mm-hmm.
do you have to add plus or minus?
One of them's plus, one of them's minus. That's where the plus or minus comes from.
I think that's
Yeah.
only if you're
If you're the one taking the square root, you have to consider plus or minus, and that's where the conjugate pairs come from. Yeah, yeah. One of them's plus and one of them's minus. Okay. Now, if you didn't factor that one all the way, there's another way you could have done this one. You could have actually said 2x minus 5 equals 0, or x squared minus 5 equals 0. And on this one, you could have said x squared equals positive 5. And now this is what you're thinking, Peyton. When you extract the square roots from both sides, when you're solving an equation by extracting the square roots, that's where you have to consider plus or minus the square root of 5. And that's, you still get your same roots that way. But I prefer you do it by the factor method. Okay? So how do we know if something's prime or not? If it's linear in the form mx plus b, or if it's a quadratic sum of two squares. Not a difference. A difference to two squares factors, even when they're not perfect squares. Okay? Let's just go ahead and say, but, we'll say, but ax squared minus b is factorable. And it factors into what? Let's go ahead and factor it in variable form. It would be the square root of ax plus the square root of b, and the square root of ax minus the square root of b. Okay? They don't have to be perfect squares, do they? We just saw that. Your first exposure to difference of squares are when there was a difference of two perfect squares. X squared minus 4 becomes x plus 2x minus 2. All right, so if I want to sketch this dude, which is ultimately our goal, right? It says I will graph the polynomial function using its real roots. Give yourself an x and y axis. Let's go ahead and plot the roots first. Here's -1. Here's -2. Here's -3. There's 1. There's 2. There's 3. All right, where is 5 halves going to live? What's another name for 5 halves?
1.5. 1.5?
No?
No, or 2.5.
2.5. 2.5. So it'd be right in the middle here, yes? What's the square root of 5 approximately?
2.5.
It's 2, yeah, it's 2 point something, right? How do we know where it is compared to 2.5? Your calculator can help you. Does anyone have a calculator?
Oh yeah.
Oh, I know where one's at. Let's go. Oh, that's my photo gallery. Sorry. I was like sharing my trips with y'all. Here I am at the beach. How do we get there? Well, anyway, just trust me. The square root of 5 is going to be less than 2.5. It's going to be right there. Okay? And then the negative square root of 5 is going to be right around here. Now we need to know the end behavior, right? What degree is this going to be?
2.
It's degree 2?
Degree 3.
It has to be degree 3 at least, right? I found 3 x-intercepts.
Oh yeah.
What is the multiplicity of each of these?
1.
They're all to the first power, right? So they're all crosses. Okay? So now I need to know the right end behavior. What's the right end behavior? If I were to take the limit as x goes to infinity of f of x, what would the leading coefficient be? If I were to FOIL this out, what would 2x times x squared give us? It would give us 2x cubed plus something, right? So what's your leading coefficient? 2. That's a sub 3. That's a positive number. So what's the right end behavior? What type of infinity? Positive infinity. Remember that? The leading coefficient sign gives you the sign of the right end behavior. Now I know that the left end behavior as x goes to negative infinity is what?
Negative.
Negative infinity, because it's an odd degree. So that must mean it comes in from the what? It comes in from the bottom. So it's going to come in from the bottom. It's going to turn around. Watch what it does here. This is going to be kind of hard to do because they're so close together. But it's going to come down. It's going to cross, and go up like that. Kind of funky, right? You don't have a lot of room to turn around and go through there, but we give ourselves enough room. That's why we draw it. We don't let the calculator draw it. If you let the calculator draw that, you're going to have to zoom in quite a bit there to see it actually looking like two different x-intercepts. Okay? All right, there you go. What's the domain of this function? All real numbers. We could have done that with our eyes closed, right? But what's the range of this function? All real numbers, because it's an odd function. We now could have done that with our eyes closed. Okay. This is the graph of f of x. So I did a little bit more than the question asked. It said to find the solutions. The problem was the over when I got to this. These are the 3 solutions to the equation when it was set equal to 0. But because I named the expression on the left f of x, I actually looked at the graph of f of x. And now I can translate it into x-intercepts. All right. So the above example gives us a rational solution, which is a fraction. We call this a rational solution because it's a ratio of two integers. And it gives us two conjugate irrational solutions. Plus or minus the square root of 5 are called irrational numbers because they don't simplify. Okay, so let's go ahead and write that. A over B plus or minus A over B. This is called a rational number because it's the ratio of two integers. And then plus or minus the square root of C, we'll use a different letter there. These are called irrational numbers. They're non-terminating, non-repeating decimals, if you remember that, right? An irrational number is a non-terminating, non-repeating decimal. So if you ever can't simplify, like the square root of 4, the square root of 4 is not irrational because that's equal to 2. But the square root of 5 doesn't simplify. We're stuck with the radical. That gives you an irrational number. Okay? And notice those irrational numbers occurred in conjugate pairs, didn't they? Plus the square root of 5 and minus the square root of 5. That's going to be a very important theorem later on. Okay? All right, so here's the rational root theorem. Back in the day, people wanted to know the answer to the question that we just answered for this one. Where is a polynomial function equal to 0? What are the roots of the polynomial? What are the x-intercepts of its graph? Okay, and they didn't have the calculator to help guide them. So if they were interested in a particular type of solution, namely if they were interested in a rational solution, by the way, is an integer a rational number? Like is 5 considered a rational number? An example would be 5 halves or 5. Why is 5 considered a rational number? Because that's the same as 5 over what? 1, yeah. So all integers are rational numbers. Rational numbers are all the integers plus all the combinations of the ratios of the integers. Those are the relatively nice numbers. They're fractions, or they're terminating decimals, or they're repeating decimals. These are terminating or repeating decimals. Like 1.333333333 is the same as 4/3. 3.14159 is irrational, right? So irrationals, these are your non-terminating, non-repeating decimals. An example would be like the square root of 5, or even pi. Pi and e themselves are irrational, but they're not algebraic irrational. They're called transcendental irrational. But like the square root of 5, the square root of 7, square root of 6, things like that. Okay, square root of 6. Those are the ones we're kind of interested in right now. Square root of 10, stuff like that. We're not really interested in pi and e right now. Okay, those are called transcendental. We're interested in the algebraic ones, the square root of a number that doesn't simplify. Non-terminating, non-repeating decimals. Okay, so if we're interested in the rational type of solutions, that is the relatively nice solutions that are fractions, that are terminating or repeating decimals, for any polynomial, we know they're going to be in a certain form. Okay, they're going to be in the form p over q, where p is a factor of the constant a sub o, and q is a factor of the leading coefficient a sub n. Okay, if you know that if you are expecting to have rational solutions, they're going to be of the form p over q, where p is a factor of the constant and q is a factor of the leading coefficient. Okay. Now notice the theorem does not guarantee that you're going to have a rational solution. All it says is if the equation has a rational solution, it's going to look like that. Okay. So what it does is it gives you a list of possible candidates to try out to see if they actually work. Okay. Rather than trying arbitrary numbers, you have a list of candidates to try out. If none of those candidates work, then all the solutions, if they're not rational, have to end up being irrational. Let me show you what I mean. Find the rational roots of x cubed minus 3x plus 2. Be sure to list all distinct possible rational roots and then try them out individually. Okay. Does this thing factor, first of all? Does it factor into something like we're used to, like double bubble? Why not? It's x cubed, right? If it were x squared, if this were just x squared minus 3x plus 2, I know that it would factor into x minus 2, x minus 1. Yes, yes? And my solutions would be x equals 2 and x equals 1. Okay? Well, let's look at that. Are x equals 2 and x equals 1, are those rational solutions? They are. So looking at the theorem that we just saw above, this is your a sub 2, your leading coefficient, and this is your a sub 0, your constant. It says that any possible rational solution is going to be of the form P over Q, where P is a factor of a sub O. What are the factors of 2? Plus or minus 1 and plus or minus 2, right? What are the factors of Q, the leading coefficient? Plus or minus 1. Yes, yes? So if I look at all the combinations of P over Q now, this is actually Q, and this is P. The combinations are going to be plus or minus 1 over 1 and plus or minus 2 over 1, which means they're going to be plus or minus 1 or plus or minus 2. Where my two solutions here, one of those four, my solution was a 2, right, which was in my candidate list, and my other solution was a 1, which was also in my candidate list. So that's what the theorem tells you. If you are going to have nice rational solutions, either integer or fractions, they're going to be in that candidate list right there. We had 4 candidates, and 2 of them worked, okay? Well, guess what? If it's x cubed minus 3x plus 2 and it doesn't factor, we are still going to list the possible rational solutions. So here's what we would do. We would do the exact same thing. We would identify the leading coefficient. Let's just do it again. The leading coefficient is 1. That's what we're calling Q. And then this back here is what we're calling P. Okay? That's your constant. So let's list the factors of 2 first. These are your P values. Okay, you're going to do plus or minus 1 and plus or minus 2. Those are the only 4 factors of 2. Would you agree? Integer factors of 2? Plus or minus 1, we could do negative or positive, and plus or minus 2. And the same thing with Q. The leading coefficient is 1, so it's plus or minus 1. That's it. Now, to list the combinations of P over Q, all you have to do is do what we did above. You just take the it's like you're distributing. You're doing 1 over 1 and then 2 over 1. And you only need the plus or minus 1 time. The ratio is either positive or negative. So we'll say plus or minus 1 over 1 and plus or minus 2 over 1. And that simplifies to plus or minus 1 and plus or minus 2. So we have 4 candidates or 4 possible rational solutions. I spelled soul wrong. Soul, S-O-U-L, soul. Okay, so how are we going to determine now if any one of those 4 actually work if we can't factor it? Can I try them out? Trial and error, yeah. Let's try them out. Let's try them out. We're going to do let's do f of 1 first. Let's see if it works. F of 1. That's going to be 1 minus 3 plus 2. What does that give us? That gives us 0, doesn't it? So x equals 1. Congratulations, you worked. Let's try f of negative 1. F of negative 1. We're going to get negative 1 cubed is negative 1. Now we're going to get plus 3 plus 2. Does that work? That equals 4. So x equals negative 1. Sorry, you don't work. How about f of 2? Let's try f of 2. 2 cubed is 8. 3 times 2 is 6 plus 2. That's 8 minus 6. That's 2 plus 2, which is 4. Does that work? No, it doesn't work. Okay, how about a negative 2? Let's try a negative 2. Negative 2 cubed is negative 8. And then we're going to get plus 6 plus 2. That gives us 0. Yay, so x equals negative 2 works. Correct. Nice. All right, so how many distinct real solutions did I find? 2. Okay. I found of the candidates, of the 4 possible rational solutions, 2 actually worked. So I know that I have roots. I can list them now as x equals 1 and x equals negative 2. Now, here's the problem. It's a cubic polynomial, isn't it? How many x-intercepts maximum can it have? 3. I just found 2 of them. Is there another one out there somewhere? Or does one of those count twice? Do we know that information yet? No. Pooper scooper. Well, is there a way? Can y'all think of a way that we can figure out what the other root is if I know 2 of the 3? How would we graph it? In order to graph it, I would have to know all the roots because I'd have to know their multiplicities, right? One of those certainly can count twice, correct? One of those could be a double root. But we could have another irrational root out there, like the square root of 5 or something like that. Hey, I got an idea. Y'all know about division? Let's try division, okay? Let's use the factor theorem. If x equals 1 is a root, what's the corresponding factor? No, x minus 1 is a factor. And if x equals negative 2 is the root, what's the corresponding factor? No, x plus 2 is a factor. Yeah. Now, let's see what I'm trying to do here. Here's an example. Let's say I have 14, and I know that x equals 2 is a factor. Is there a way to figure out the other factor of 14 if I know 2 is a factor? How? I divide. 14 divided by 2. 2 goes into 14 how many times? 7. This is my quotient, which is the other factor. Yes? The other factor. Can I not do the same thing with polynomials? If I know a factor, can't I divide it out of the original problem that I have, like I did for 14?
Yeah.
The answer is heck yeah. All right, let's try that out. What does long division look like? Well, let's come over here. New column. We're going to do x cubed minus 3x plus 2. X cubed minus 3x plus 2. And we are going to divide out. Which one do you want to divide out first? The x minus 1 or the x plus 2? Let's do the x minus 1. Okay. Have we seen this before? Do we know how to divide polynomials?
Yeah.
Yes, we do. We certainly do. We look at this, and we ask ourselves, how many times does x go into x cubed? Or in other words, what is x cubed divided by x? We're doing x cubed divided by x. That's what we're doing. What is that equal to? X squared. No, it's x squared. X cubed divided by x is x squared.
Yeah.
We better know that on a Monday morning.
Oh yeah.
What's x cubed divided by x? X squared. Or in other words, how many times does x go into x cubed? X squared times. So we do that first. And notice I did this off to the side. This is my workbench over here. Now I distribute from up top to both of those. Remember that? Let's distribute. What's x squared times x? We multiply. I get x cubed. I write it under there. That should be the same at this point, right? If those are different, then you did your first step wrong. Now what's x squared times negative 1? Negative x squared. Okay? I write it there, and now I have to subtract. When I subtract, I have to change both signs. Okay? Well, you can put a placeholder. We're just going to be mindful that there's not another x squared term. If you want to put a placeholder, you can. Change both sides. All right, now what's x cubed minus x cubed? 0. Is there another x squared term up above to add to my x squared term? No. So this is just x squared, and then I bring down the minus 3x plus 2. That's why if you want to have a placeholder, you can, or you just know you can't add like terms. I mean, you can only add like terms. All right, now we do it again. How many times does x go into x squared? Well, what's x squared divided by x? X times. So this becomes plus x. And I distribute from up top. What's x times x? X squared. What's x times negative 1? Negative x. Okay, good. And now I subtract, so what do I do to both sides? I change both signs. We're subtracting, so we distribute the negative. Now we add. What's x squared minus x squared? 0. But now I have like terms. What's negative 3x plus x? Negative 3x plus x is negative 2x, and then I bring down the plus 2. And I do it one more time now. How many times does x go into negative 2x? Or off to the side, what's negative 2x divided by x? Negative 2, so I put minus 2 up here. And now I distribute again. What's negative 2 times x? Negative 2x. What's negative 2 times negative 1? Positive 2. And now I subtract, so I change both signs. What do I get at the bottom? That's my remainder. Is that reasonable to get a remainder when you divide something by one of its factors? Yeah, when we divided the 14 by 2, we got 7, remainder 0. That just proves that x minus 1 is a factor. That just proves that x equals 1 is a root, doesn't it? Okay, so here's what we know. Now we know this. We know this. We know that x cubed minus 3x plus 2, we know it equals x minus 1 times the quotient x squared plus x minus 2. Yes, yes? That's what we just proved. We found the other factor. It's x squared plus x minus 2. Now we could do we could do long division again with the other factor. What's the other factor that we still know? X plus 2, right? We could do long division with the quotient x squared plus x minus 2, and we could factor out the x plus 2 using long division again. Or we could do this. Once you get it down to a quadratic, we have a quadratic right here. Aren't we home free?
No.
Well, once we get down to a quadratic, we are home free because either A, we know how to factor it, like we would have done in the beginning, or if you're really interested in the roots and you can't factor it, don't we all still know the quadratic formula? We all still know the quadratic formula. Now let's see if this one factors. I hope it factors. Okay. In fact, I know it factors. What's one of the factors?
It should be the
It should be one of the remaining factors that we know. X plus 2 times x. What's the other one? X minus 1. Ah! This is really x minus 1 squared times x plus 2. Yes, yes? Now that I have it completely factored, I can do a better job of listing the roots, can't I? Because now I can say the roots are x equals 1, multiplicity what? 2, and x equals what? Negative 2, multiplicity 1. Ah, so I already knew both roots. I just didn't know that I had both roots, the only two roots. I didn't know which one, if any, was a bounce, a double root, and now I do. And now I can sketch the graph. Let's sketch the graph. Here's 1. Here's negative 2. That's the bounce. There's where it crosses. Do we know the end behavior, the original function?
yeah.
Yeah, what's the right end behavior? What's the limit as x goes to infinity of f of x? Infinity, and because it's an odd degree, what's the limit as x goes to negative infinity of f? Negative infinity. So it comes in the...
Even degree because it's
No, it's x cubed. It says right there, it's x cubed.
the other x, right?
When it's not factored like that.
No, we have it factored right here. What's the sum of the multiplicities? 2 plus 1 is 3. It's a cubic.
When it's like this, you just pick the biggest degree.
Yeah, when it's in expanded form, in standard form we call it, it's just your largest exponent.
I
Yeah.
thought you added.
It's only no. I see what you're saying. We don't add that 3 into 1 because it's in standard form. In standard form, it's just the leading term. If it's in factored form, right over here in factored form, then we add the degrees. Whoa, easy boy, easy. It's 2 plus 1, which is 3. Okay, so now we know what the graph looks like. It comes in the bottom, crosses through at negative 2, and what does it do at 1? It bounces, and it looks like that.
That wasn't very fun.
What do you mean that wasn't very fun?
The last.
It's almost like we need more space to do that kind of problem, right? What was your least favorite part of all that? The long division? That's what most people say. That's what most people say. The long division is their least favorite part. What if I told you we can do that division a different way, a more synthetic way that you would be more pleasing? Would you be up for it?
If it's linear, you can like divide it.
Yeah, let me tell you something about synthetic division. Synthetic division, this is what we're going to do. We're not actually going to do long division. When you're dividing by a linear factor, as you just said, Brady, we're going to do synthetic division. Here's what you do. You first write out the coefficients of your quotient. And now you need a placeholder, okay? So you get 1 x cubed, 0x squared, negative 3x, and 2, okay? These are the coefficients, only the coefficients of your function. And you do need a placeholder, okay? Now leave a space underneath for another row and put a box out front here and put a box out here on the back end. This we know is going to be 0, okay? Now when you synthetically divide, you don't synthetically divide with the factor, you synthetically divide with the root. So what's the root of x minus 1? X plus x equals 1, okay? So this is the root. We put the root right there. We synthetically divide with the root. Now here's the process. Are you ready? We bring down the first number every time. You just bring it down, okay? And then you're going to multiply along the bottom times that root. What's 1 times 1? 1. You slide it up here, and now you add vertically in the columns. What's 0 plus 1? 1. And you do it again. What's 1 times 1? 1. You slide it up, and now you add vertically. What's negative 3 plus 1? Negative 2. And if you multiply it one last time, what's 1 times negative 2? Negative 2. You slide it up and you add, and what do you get? You get 0. Guess what these numbers are right here?
X squared plus.
Those are the coefficients of your quotient. Isn't that what we got over here on the top?
Yeah.
We got a 1x squared plus a 1x minus 2. Yeah. Now watch this. Here's the cool part. You could actually keep going. If you wanted to keep going, didn't we know another root?
Yeah.
We knew another root to be what?
2.
Negative 2, actually. Negative 2. We can continue synthetically dividing. Let's divide on our result here. Okay? So we'll just put a negative 2 right there. And now we bring down this 1, and we multiply and we get negative 2. We add, we get negative 1. We multiply and we get 2. And we add and we get 0. These now are the coefficients of your mx plus b factor.
X minus 1.
So you just get 1x minus 1. And if you set that equal to 0, what is your last root? X equals 1. And now you can see that 1 was a double root. That's how we're going to do these problems. We're going to synthetically divide them instead of long divide them. We'll do a lot more of that in this section and especially in section 3.4. So I had to show you the long division first, didn't I? So that you can appreciate what we're doing and appreciate the synthetic process. All right.